Okay, hey everyone, this is take two, at least, take two of this video. The first one I loaded up to Canvas seemed unplayable. So here goes again. Carbon cycle, radiation, albedo, other controls on Earth's climate system. Trying to think of the fundamentals of the climate system. And let's start here. There are laws in science and there are facts that we need to understand and accept. So what are some about Earth's climate system? What are some facts or truths or laws about Earth's climate system? Not the interpretive aspects, not how much will sea level rise in the next century, but rather concepts like if you burn fossil fuels, the mere chemistry of the reaction, the thermodynamic and kinetic controls of nature say if you burn fossil fuels, hydrocarbons, you get CO2. Unquestionably. You can measure greenhouse gases like CO2 or methane or nitrous oxide in the atmosphere. We can measure these gases in the atmosphere and they are increasing. That is a fact. Another fact based on laws of nature is that greenhouse gases are infrared active. In other words, greenhouse gases absorb heat. In other words, greenhouse gases in the atmosphere absorb heat. And they are increasing because we are burning fossil fuels. Therefore, burning fossil fuels is causing the amount of heat in the atmosphere to increase, i.e., it's warming. Nobody can deny the fact that burning fossil fuels will increase the heat trapping capacity of our atmosphere. Another one that I think is important is that the increased partial pressure of a gas in air increases its concentration in solution. And this is important because as the concentration of CO2 in the atmosphere increases, that causes CO2 to diffuse into the oceans in solution. This is part of Henry's law. It's just a law. So burning fossil fuels causing greenhouse gases to increase in the atmosphere will cause those greenhouse gases to dissolve in the oceans by Henry's law. It's not open to interpretation. We are forcing CO2 into the oceans. And that is making them become less alkaline. You might say that they are acidifying. Probably technically, since their pH, the pH of seawater is around 8.0. It's alkaline. It's on the basic side of 7. So technically, the alkalinity of the oceans is decreasing. Often it's referred to colloquially as ocean acidification. CO2 dissolving in seawater will make some acid. Another fact, if you believe in like the science of physics or astronomy, is that solar variability is for sure less than 10% of increased global greenhouse gas emissions. So the sun may have some cyclicity where it puts out a little more and a little less energy and some flares and solar spots and so forth. But the net effect of any possible increase of energy coming from the sun is far overwhelmed by the greenhouse gas increases that humans have placed on our atmosphere. You can measure sea level. We'll look at tide data. It's risen about 22 centimeters so far over the last 140 years or so. It's measurable. Rising sea level, okay, then it gets maybe a little interpretive. 20 centimeters of sea level rise is going to create some storm surges that reach inland, but 50 centimeters of sea level rise, some interpretation into how drastic that will affect coastal climates. But the undeniable fact is that sea level is rising, and it has risen at least 20 centimeters so far since the late 1800s. The interpretive aspects get into things like future changes in sea level. How will temperature increase? What are emission scenarios for the 21st century? Some of the case studies that you are involved in right now get into some of these emission scenarios or sequestration. Will we be sequestering CO2 from the atmosphere to counteract the load of the GHGs that we've put on from combusting fossil fuels? You know, the number of intense tropical storms in a given year. We can't say in the year 2022 there are going to be 4 Category 5 tropical storms who have their origins in the southern Atlantic Ocean. We just know that the probability of those storms, those intense storms, is increasing as temperature increases, etc. We've been here before. The electromagnetic spectrum. Climate and the electromagnetic spectrum go hand in hand because on the long wavelength side of visible light, here's visible light right here, somewhere in the range of 400 to 700 nanometers, just under 1 micrometer, is where visible light is. And just to the right on that in the scale, or in terms of longer wavelengths on the order of hundreds to thousands of nanometers, is infrared radiation. When the sun shines on a nice sunny day onto a black basaltic rock and heats that black basaltic rock up, the heat that emanates from the surface is carried upwards in the form of infrared radiation. And this is the wavelength where greenhouse gases absorb heat. The sun sends us a 774 petawatts. Some of it's reflected up in the atmosphere, some of it's reflected by clouds, some of it bounces right off the Earth's surface, like off of a white snowy surface. The rest heats the Earth's surface and is re-radiated outward as infrared radiation. And the more greenhouse gases in the atmosphere, the more CO2, methane, nitrous oxide, CFCs, the more infrared is trapped and the warmer the atmosphere becomes. So this variable here, radiation absorbed by atmosphere, is increasing because humans are burning fossil fuels. We are putting CO2 and methane, especially CO2, into the atmosphere at rates that are something like 100 times what the natural geologic, biologic processes would put CO2 into the air. Perhaps if you're more into the physics or chemistry side of things, this is interesting. It shows wavelength on the x-axis, like a previous diagram that we just looked at with the visible and infrared. It shows the amount of energy that reaches the outer part of the Earth's atmosphere in the dark line here. If we look at, so there's ultraviolet radiation, that's everything to the left of this dotted line right here. This is ultraviolet radiation. A lot of it is absorbed, actually. This is how much hits the outer atmosphere. This thinner line here is the amount that actually reaches the Earth's surface, the amount of ultraviolet radiation that reaches the Earth's surface. What molecule is responsible for consuming all of that harmful ultraviolet radiation? Ozone, O3. Excuse me. Some light just gets scattered off of particles back into outer space. Some gets absorbed by greenhouse gases. Greenhouse gases will absorb infrared if it's coming in or going out. Most of the infrared that's radiated back out toward outer space from a warm Earth surface is in the 5 to 50 micron range, which is going to be well off to the right of this page. So longer wavelength radiation is what comes from the Earth surface. The wavelength is inversely proportional to temperature. So lower temperature, the very high temperature sun puts out shorter wavelength radiations, and then the Earth re-radiates back out to space longer wavelength radiation because it's a cooler body, the Earth is, than the sun. Okay, quick little quiz. What's the answer to this idea put forward? A climate skeptic says, adding more CO2 to the atmosphere will not affect infrared atmospheric absorption because the atmosphere is already saturated with respect to CO2 at, for example, 4,300 nanometers. Actually, 4,257 right here. If we look here, this is wavelength, again, in nanometers. This is in the infrared spectrum. And where does CO2 absorb infrared radiation? Well, it absorbs a little bit at around 2,000 nanometers. At pushing 3,000 nanometers, it absorbs almost all of the radiation it possibly can in that wavelength. It's very reactive in that area, so it absorbs a lot of radiation. It doesn't absorb anything around 3,000 or 4,000. Then it gets up to here, and oh, look at that. At 4257, around 4300, the amount of outgoing infrared radiation is completely absorbed by CO2. CO2 can't really absorb anymore. That's what the climate skeptic once said. The true answer is that CO2 absorbs at other wavelengths, like right here. So increasing CO2 will increase the amount of infrared absorbed. Increasing here is not going to change. There's just no absorption there. It's already saturated, basically. But increasing CO2 at all these other parts in the spectrum are going to increase the amount of infrared absorbed, i.e. heat the atmosphere. And this is a case where, like, science can be dangerous. You can have somebody spout off, especially to willing ears, CO2 is already saturated with respect to infrared absorption at 4,257 nanometers. So all of you climate wingnuts who are saying that CO2 is causing warming are wrong. Take a look at the infrared spectrum. So you just have to, have some basic knowledge to have informed responses to questions like that. C'est la vie. We talked about this earlier when we talked about basic fundamentals of the Earth system. So CO2 flexes, stretches, wobbles in the presence of wavelengths of infrared radiation of very precise wavelengths. Here's that 4257. This is just a fundamental law of nature. You can't argue that burning fossil fuels and driving around gasoline combustion cars is not going to cause the Earth to warm. It's a fundamental principle of nature. It's like gravity. It's like gravity. Say it again, it's like gravity, it's like wind, it's like pressure differences, it's like the first law of thermodynamics, some of these things you just can't argue against. You also cannot argue that greenhouse gas concentrations are increasing. I have to update this every time I teach this class. CO2 is now at 415 parts per million. The V is for volume. Gases are measured in volume basis because they more or less behave as ideal gases, blah, blah, blah. CO2 is increasing. Fixed gases like nitrogen, oxygen, argon, neon, etc. are not increasing. What else is CO2? Methane, greenhouse gas. Land use change. This is a part of natural gas, so any leaks will put methane into the atmosphere. It's more than doubled. And nitrous oxide, major agricultural byproduct. So much nitrogen fertilizer, so much nitrogen in manure. So agriculture is a major source of nitrous oxide, and it has increased, as to be updated every time I teach the class. You can look up this information. A lot of this stuff is cited throughout the presentation, so you can look things up. Carbon cycle. Seen cycles before? I hope you're not sick of cycles. This cycle has reservoirs, atmosphere, shallow ocean, deep ocean. Sediments on the seafloor. Sediments that have become buried and thrust or just buried deep within the earth, called the crust on this diagram. Lithosphere would be a more or less equivalent term on this diagram, or the solid earth. There's terrestrial ecosystems, biota, like trees or microbes, soils, like humus and soils. There's a lot stored in peat bogs, like wetlands. And then there's the atmospheric reservoir, and that's the cycle. The unit here is petagrams, which is the same thing as a gigaton. And the fluxes here are in petagrams per year or gigatons per year. And the bold numbers show where the cycle is most affected by anthropogenic activity. Point 1 here is the background, sort of natural flux. Probably you could say the pre-anthropogenic flux. About 0.1 gigatons per year fluxed into the atmosphere. Now it's around 10 gigatons per year, 10 petagrams per year. This is what we're doing. We're taking hydrocarbons, we're taking coal out of the lithosphere of the Earth, or out of the crust of the Earth, and putting them into the atmosphere. The atmosphere has increased. This number when I first started teaching this class was in the 700s. Maybe even it was in the high 600s, probably like 120 years ago or something, like 1880 or 1900. So this reservoir has increased. It has increased about 30%. Increasing concentrations of CO2 in the atmosphere means CO2 is going to diffuse into the oceans. And that is this bold 92 here. The normal pre-anthropogenic flux was 90 in, 90 out. 90 petagrams of carbon, mostly as CO2, dissolve into the oceans or get photosynthesized in, and then some goes back out. And you basically have, like pre-anthropogenic, a nice steady state, kind of like an equilibrium had been established. But we are tweaking the equilibrium by loading the atmosphere with all the crap that comes out of coal-fired power plants and tailpipes and things like that. And by Henry's law, CO2 will diffuse into the water, the aqueous solution that it's in contact with, and that means that the oceans are accumulating CO2, and that is driving us towards what I fear is a threshold in terms of marine ecosystems. We'll dig into that a little more later. So yeah, fluxes and reservoirs. Press pause, look at it. This is from a textbook that I just had come out last year. You might find slightly different numbers elsewhere, but this is as close as I could come to a nice, accurate summary of the carbon cycle and really thinking about fluxes. If you want to solve the problem, what do? It's too much in the atmosphere, suck it back out of the atmosphere. That's called sequestration. There's too much fluxing into the atmosphere, cut it off. That would be called emissions reduction. So putting an X through that nasty 9.9 there is part of the problem. Increasing this 125 here is also part of the solution because it gets at decreasing the supply and it also increases the flux out of the atmosphere. And increasing the flux out of the atmosphere and decreasing this number is going to start pulling CO2 back out of the oceans. And ideally fixing it back into terrestrial ecosystems or into the lithosphere of the Earth by various types of sequestration. You can read later this week, as soon as everything rolls in, maybe even by tomorrow, Wednesday, some cool case studies about sequestration. Okay, onward. Albedo is reflectivity. Goes from 0 to 1 or 0 to 100, depending if you multiply by 100 or not. This one shows some of the basic principles. The snowy, cold northern hemisphere has relatively high albedo, high reflectivity because it's white snow. What about the Sahara? Why does Sahara Desert have such high albedo? Anyone? Yeah, white sands, light-colored sands, highly reflective. Ironically, if the Sahara were to become vegetated, its reflectivity would go down and its absorptive capacity would go up. Right. The real issue here is that the more sunlight that's reflected, the less warming. The lower the albedo, i.e. the lower the reflectivity, the more heat is absorbed. So as the north warms and snow caps melt, more black soil is exposed or dark seawater is exposed. Dark seawater absorbs much more incoming solar radiation than does exposed ice or snow. The diagram on the bottom right shows it schematically as well. Press pause and look at it if you want. So yeah, albedo is the reflectivity of a substance, sometimes called the reflection coefficient. Values range from 0 to 1 on this chart here. You can see that snow got a value of like 0.8, 0.9, quite high reflectivity. Something dark like water, like seawater, has higher absorptive capacity, lower reflectivity. Dark plant soils, dark peat soils, for example. Those peat soils have the capacity to absorb a lot more heat than the snow that just melted off the surface. These are values that go into climate models. So when you start thinking about climate models, reflectivity, how much of the incoming sunlight is reflected, is a very important one. What's another important variable that you would put in a climate model? Yeah, greenhouse gas, that radiative forcing, the capacity to absorb infrared. So those are a couple variables that are important, and this is one. High values mean high reflectivity. What is reflected? Incoming solar radiation. And albedo of Earth is decreasing. And part of predictions for global warming models incorporate the fact that, especially in the large terrestrial and also like frozen seas of the northern hemisphere, the albedo is decreasing because net snowmelt is occurring. This is just an example of a study published 15 years ago using satellite data. We'll look at some other examples too. Just some photos of albedo and just thinking about, very high albedo in the snowfield up here, very low albedo where my wife Maggie is standing on this darker landscape in the surface. The longer the snow stays in the Sierra Nevada mountains of southern Spain, the cooler this environment is. And it's tangible, it's tactile. You can feel it down in the valley. If there's snow up in the mountains, the cold air that sits on top of the snow sinks down because it's dense and keeps Granada down there in the valley a lot cooler. So if climate change decreases the snowpack in the Sierra Nevadas, Granada could get a lot hotter, a lot hotter. And that has reached temperatures in the high 40s centigrade during periods of late July and August when there's no snow left. Otherwise, it would probably be in the high 30s. It's a big difference. So local climate effects and global climate effects. Here's an example of ice breakup where you can see the dark water having a lower albedo, lower reflectivity, more absorption. Arctic sea ice is decreasing. This is empirical, i.e. measured, i.e. based on measurements. You could forecast this outward and maybe predict that by, the mid to late 21st century, there will be no sea ice left. But I went to a talk last fall where it says it's going to go somewhat, curve's going to kind of flatten out somewhat. Whatever the case, it's not headed in the right direction. Got to turn that around. Talk about feedbacks. A positive feedback is an amplification of an effect. A good example being melting polar ice that exposes dark ocean with lower albedo. That's going to cause more heat to be trapped. It causes more melting. More melting means more exposed dark ocean, which means more absorption of heat, more melting, etc. Yale's got some examples on their environment website. Others? Anyone? Wish we were in the classroom right now. But this is all right, I guess. How about some others? Warming oceans and the solubility of CO2. The oceans have taken up, give or take, something like 50% of the CO2 that humans have emitted by combustion of fossil fuels and other sources. Burning of biomass, the making of cement puts CO2 in the atmosphere. Well, the oceans have absorbed a lot, but if the oceans warm, the solubility of a gas in solution in water decreases as temperature increases. So solubility is inversely proportional to temperature. So if the oceans warm, if the surface of the oceans in particular warms, it has less capacity to hold dissolved CO2, which means CO2 might be released to the atmosphere from a little trigger of warming. Now there's a little more CO2 in the atmosphere, so that's going to absorb more heat in the atmosphere, which is going to heat the oceans, which are going to release more CO2 to the atmosphere. So that could be a feedback loop that we might be concerned about. And others? Exactly what I was thinking about too. Warming gelisols, i.e. permafrost soils, will release CO2 and methane. Methane, CH4 here, and CO2, carbon dioxide. Warming permafrost. So you melt some snow up in northern Alaska, northern Siberia. The permafrost in the soils are now, dark soils exposed to the sun. The permanent ice that's in those soils starts melting, releases CO2 and methane to the atmosphere. They're greenhouse gases. They cause warming, which causes more melting in the north, which causes more black soils to be exposed, which causes more CO2 and methane to be released to the atmosphere, et cetera, et cetera, et cetera. So these are feedbacks that we need to be very concerned about, especially this bottom one. Circle it in red, that one. If only there were some good negative feedbacks in the climate system that would dampen the effect. But they tend to be pretty slow. The kinetics, i.e. the time factor, the reaction rate factor, the kinetics of these negative feedbacks dictate that they occur much more slowly than the positive feedbacks we just looked at. And, some things like there's just reaction rate, and like rainwater with dissolved CO2 in it naturally can break down calcium carbonate and limestone. Dissolved calcium ion, dissolved bicarbonate, they maybe go to the oceans, become ocean sediments, and get buried into the lithosphere of the earth. So you could say that if CO2 were rising, that's going to push the reaction to the right by Le Chatelier's principle. So pushing the reaction to the right is basically taking CO2 and converting it to bicarbonate and maybe burying it in the oceans. And so the increasing CO2 in the atmosphere would be countered by it reacting with calcium carbonate and turning into something else. So you increase CO2, but it ends up not increasing so much because it keeps getting consumed by weathering reactions. But it's a very slow process. More geological time kind of process. But it does possibly inform us of one avenue of sequestration that we might undertake. In other words, if there are ways that we can figure out how to get CO2 dissolved in water to react with minerals to fix CO2 into a non-gaseous state, that could be one pathway to sequestration, and one of the case studies summarized for you all covers this. Increased CO2. CO2 is an ingredient, is a reactant in photosynthesis, so increasing CO2 should increase photosynthesis. Increasing temperature should increase cloudiness, which would increase reflectivity, which might make more sunlight bounce off clouds and go back to outer space. These are complicated. Clouds are complicated. Some clouds reflect, some clouds actually trap heat. And photosynthesis is complicated because while you could theoretically predict that increasing CO2 will increase photosynthetic rates, other complicating factors like changing precipitation patterns, desertification, factors that are part of the complex web of the natural world mean this is not a simple relationship. If it were, perhaps there'd be less CO2 in the atmosphere. Let's look in the paleoclimate record, see what we can see about feedback loops. First of all, let's just look at the paleoclimate record. In principle, this is from Petit et al. Here's their article, published in the journal Nature in 1999. One of the first, maybe not the first, but to me it came at a time when ice core science was becoming really important in trying to understand climate change. Okay, I'll say that. And what is plotted here? This is today. This is 50,000 years ago, 100,000 years ago. Ka means kilo annum, so 200 kilo annum is 200,000 years. So we're looking at ice age cycles here. That's the time scale. And then on the y-axis is incoming solar radiation. We'll come back to that. A couple of different stable isotope values. We'll come back to those. Temperature, we'll come back to how that's figured out. And then these two greenhouse gases. These are actually directly measured. Their concentrations are directly measured from bubbles trapped in the ice. Ice that was once snow. Snow that fell, let's say, 300,000 years ago, and more snow fell on top of it, and more snow fell on top of it, and it compressed the snow down, and some of the air got trapped in there, and now is bubbles inside the ice that's been deeply compressed under hundreds to thousands of meters of ice sometimes. Eons, millennia of accumulation of snow and ice trap air. So what we can see about the direct measurements of CO2 from these air bubbles is that, so here is concentration of CO2 in ppmv. Here we are now. Here, I guess we were in 2011. Here we are now. 450. Here's 420. We're like right here. 415. One of the things that this Petit et al. Study demonstrated to me is we're getting way outside of the comfort zone here. I mean, this is human evolution timescale. Neanderthals were around, back in here. So kind of during an interglacial period, CO2 tended to peak out at 280 ppm. It would drop out at around 180 or bottom out at 180, come back up to around 280 or 290, drop down to about 180 or 190, come back up, back down, up, down, up. Methane follows a pretty similar trend. Methane now is, the methane scales over here from 0.4. So methane, okay, right. Methane, historically, geologic time-wise, would range from like 0.4 to 0.7 or 0.8 ppb, parts per billion. Sorry, that should be ppm. Yep, I think that should be ppm. In any case, these two greenhouse gases track each other pretty well. During interglacial periods, they peak out and then they drop down. Temperature comes from stable isotopes of water. If we were all together, we might talk about this a little bit. I'm not going to present information on exactly how this works. Water has, in brief, H2O has two elements, hydrogen and oxygen, and each of them have a stable isotope that is heavier than the dominant isotope. So oxygen, most oxygen is 16, but some oxygen atoms have a mass of 18. And that difference in mass causes them to evaporate differently and condense differently depending on climate. And you can get temperature of snow or ice that fell as rain or snow based on the isotopic composition of the H2O. And what you see is that temperature, temperature, positively correlated with greenhouse gases or no? Yes, quite correlated. Boom, boom, etc., etc. And in terms of feedback loops, one thing that I think is important is that if we look at temperature, this would have been an ice age about 150,000 years ago. When that ice age ended and feedback loops started kicking in, and the Earth started warming again, it warmed very rapidly. And then it cooled somewhat more slowly, and then rapid, and then some fluctuations. But eventually the path all the way back down to a cold Earth takes a lot longer than the path from a cold Earth to a warm Earth, a non-glacial or interglacial Earth. These are those feedback loops. These are the feedback loops that are tied into, for example, you start melting the land surface and exposing black soil that has low albedo. It absorbs heat, gives off greenhouse gases as the organic matter in the soils decomposes. And so what you see here is some very major spikes that are associated with temperature rises. The temperature drops tend to occur much more slowly. At least that's what Earth's history would tell us. It would tell us that fighting the temperature increases that we are experiencing now, we're like up here somewhere, fighting the temperature increase is going to be hard because natural history tells us that Earth's temperature tends to cool much more slowly. So we might as well head it off at the pass and get our act together right now. That's my political statement. This is insolation down here. This is the amount of sunlight that reaches, it's basically the amount of sunlight that reaches the Earth. And it varies based on, a large control on this is astronomical factors like the tilt of the Earth, the wobble of the Earth as it rotates, the orbit of the Earth. Sometimes Earth's orbit puts it farther away from the sun during the winter time in the northern hemisphere, and that causes ice sheets to grow. Sometimes called orbital variations, the orbit of the Earth changing, that affects incoming solar radiation. Sometimes they're called Milankovitch cycles, named after the Serbian mathematician who discovered them 100 plus years ago. Okay, some lessons learned. Time to march forward. Yeah, you can measure CO2. People have been measuring CO2 continuously since the late 1950s at Mauna Loa Observatory in Hawaii. And inexorably, undoubtedly, it's going up. I downloaded this Monday. Today's Wednesday, take 2 of this video lecture. And temperature has increased. This would be an index that incorporates ocean temperatures and land temperatures from NASA. And what often in the United States and other places too sometimes, the time span from like 1950 to 1980 or 1960 to 1990 is often used as a reference, and like everything, yeah, it's just like saying the temperature average of 2 or 3 decades in the mid 20th century is going to be our reference value, and anything that's lower than that would just be below 0. So what we see is that Earth's temperature, more or less, with some exceptions, has increased as CO2 has increased in the atmosphere. And the decrease here, I don't know if there's a scientific consensus on it. I think a lot of it's related to sulfate pollution from coal combustion before air quality controls were enacted in the 70s and 80s. Took the sulfate out of the air, stopped acid rain, more or less, or helped to combat acid rain, but also took some scattering capacity of the atmosphere out. Maybe unintentionally, our pollution was helping to hold off warming for a little while. Why does this do this? This red line is monthly measurements. January, February, March, April, May, June, July, August, September, October, November, December. January, February, March, April, May, June, July, August, September. June, July, August, September, etc., etc. June, July, August, and September. What's going? So the black line here is a more long-term running average with this cyclic pattern taken out. Let's talk about the cyclic pattern, not just the overall like long-term average. What's the cause of this cyclic pattern? In particular, let's describe it. If you had to describe this cyclic pattern, what would you say? You would say CO2 in the atmosphere tends to increase January, February, March, April, May during the winter, in maybe spring in the northern hemisphere, and then June, July, August, September during the main growing season in the northern hemisphere. As it turns out, CO2 drops, and then October, November, December, January, February, March, April, May. And then I'm just looking outside and everything's leafing out right now all over the place in Vermont and all over the northern hemisphere where the majority of land is on Earth. CO2 is being sucked out of the atmosphere. But because we keep emitting every year, the peak is a little higher and the valley is a little higher than the previous year. But it does demonstrate to me the profound capacity of Earth's ecosystems to take in CO2. What if we could harness that a little bit? Thinking about sequestration of carbon in soils, managing agricultural soils to be carbon sinks. It's possible. Carbon dioxide, nitrous oxide, methane, chlorofluorocarbons, and hydrochlorofluorocarbons, and now hydrofluorocarbons, are all greenhouse gases. 2 of them are no longer increasing in the atmosphere. They're actually starting to decrease, these CFCs. They were banned by the Montreal Protocol starting in 1987 in subsequent amendments and so forth. They are the compounds that were destroying ozone, well, still are, because there's still an obvious legacy of 20th century behavior and an obvious lag as well. They're pretty stable. Take a while to break down here in the troposphere, and those that get up to the stratosphere tend to create havoc for a while before they finally break down. So in terms of thinking about the carbon cycle, diagram earlier, these are all those fluxes that are contributing to the increased heat trapping capacity of the atmosphere. Sea level, you can measure it. Tide gauges. Again, this is from IPCC. It looks like here the zero is somewhere like the average of 1960s or something like that. So we can see that sea level was maybe 120 millimeters lower in 1880 compared to 1960. Here in 2020, it's like 50 or so centimeters above what it was in 1960. So about 200 or 220 or 230 millimeters. Sorry, folks. 140 plus like 60 or 70 makes 200 or 210 or something like that millimeters, which is about 20 or 22 centimeters, which is something like 8 or 9 inches or something like that. Right. This is data from Australia, CSIRO, Commonwealth Scientific and Industrial Research Organization, I think is what it stands for. Well, this shows the same thing, except their zero line is 1880. And we're up to like 22, 23 centimeters, or 220 or 230 millimeters. Project that. Like if you're a scientist or somebody asks you what's sea level going to do in the future, is it going to continue to rise? It's pretty... I don't know. Would you say this is linear? Would you say it's starting to go exponential a little bit? Models are a big part of helping to forecast because who knows, is there a threshold coming up here? Mere extrapolation doesn't give us the whole answer. I can't play this video for you. I think that's what happened when I loaded up the first version. So go to this site just go to Google or go to YouTube and type CO2 pump handle and you'll get it. And what you'll see, I don't want to tell you too much what you'll see, but what you'll see is that I'll tell you the basics. We go from the South Pole to the equator to the North Pole. So this is the Northern Hemisphere, Southern Hemisphere. And this is CO2 concentration in ppm. And over time, we'll see that this bar is going to keep going up because CO2 concentrations are increasing. But the clock over here runs annual cycles. It keeps just going around year after year after year, 1979, 80, 81, 82, 83. So it's called the pump handle because as the whole bar, the whole line here goes up, in the winter time, it's like this. And then in the summertime, it sways down because the northern hemisphere is fixing so much CO2. So watch it. It also then takes us back through the ice ages, and I think it's a really useful one. I wish I could just do it and annotate it and talk over it here, but maybe you'll enjoy it more just watching it on your own. Getting close to the end here. Radiative forcing by emissions and drivers. Radiative forcing, what's that? Well, it's the heat trapping capacity of Earth's atmosphere. So that's what we're looking at here. And so we're looking at emissions, emitted compounds, CO2, methane, halocarbons, CFCs mainly, nitrous oxide emitted from agriculture to a large extent, carbon monoxide, volatile organic compounds like BTEX, gasoline kind of stuff, nitrogen oxides, which are emitted by combustion mostly, aerosols, and the precursors to aerosols. So aerosols are tiny little particles in the atmosphere. And shown here is radiative forcing relative to the year 1750 in watts per meter squared. So anything that goes to the right is adding to increased radiative forcing. In other words, heating up the Earth. And anything that goes to the left does the opposite. Let's just work down. CO2. Excuse me. If anybody were to ask you, you could say that the radiative forcing of CO2, attributed to CO2, since 1750 has increased about 1.5 to 2 watts per meter squared. Take that, climate skeptic. What do you make of that? Um, methane, water, methane and water, ozone. Sorry, here's methane. Here's ozone from like urban smog. Methane, like leaks from natural gas or wetlands or something. Less than CO2, but not insignificant. The chlorofluorocarbons are significant, but also less, and then even less so, but also something that we would seek to target. We do seek to target is nitrous oxide emissions. We can see that I don't know why methane shows up over here. I have to admit, I do not know why methane would show up as an atmospheric driver that would be on the left side of this line. Well, I may look that up and get it back to you. Maybe it'll just be one of those unanswered things that happens in a class sometimes. Interestingly, aerosols behavior depends on the composition of the aerosol. Black carbon, like soot from fires or diesel smoke, kerosene fires, kerosene like jet engines, black smoke comes out of jet engines, that absorbs incoming solar radiation. Most other aerosols or particulates in the atmosphere scatter, reflect, like behave like clouds or something. They reflect the atmosphere back out into outer space, including sulfates, and we'll look at an example of sulfates. Clouds have a generally believed to be more reflective than absorptive in terms of heat. We see albedo change here, not going in the right direction. Probably going to continue to go this way as things melt. Here's the change in solar irradiance. So my old friend that I play music with, a bit of a climate skeptic, I guess, and he said something about solar radiation, and I was like, you're an engineer. Solar radiation has increased like maybe, I don't know, 0.1 watts per meter squared. The CO2 emissions have increased like at least 10, if not 100 times the effect of the solar radiation, Rick. Look it up. You're an engineer. It's numbers. It's just numbers. Maybe you don't want people to take away your pickup truck, but, I mean, you can't deny basic science. You may not want to die, but you're going to grow older. You just can't deny it. Some things you just can't deny. I think I've been giving these video presentations too long. I'm losing my marbles a little. All right, sorry, folks, but I'm not going to start over. Yeah, so sulfates have the ability to cool. Sulfates are little particles that consist of a sulfur atom and then 4 tetrahedrally coordinated oxygen atoms. And they are naturally emitted by big volcanic explosions. Various sulfur gases are relatively abundant in volcanic systems. Sometimes if you go to like a volcanic geothermal hot spring kind of environment, you can smell a rotten egg gas, sulfur gas. That would be a different form of sulfur gas. That'd be hydrogen sulfide. This is the oxidized form that it eventually gets to in the atmosphere. Nice tetrahedral molecule that reflects sunlight. Incoming sunlight hits a SO4 and bounces back towards outer space. So it's said to that behaves as a scatterer, or it scatters incoming radiation. Also, clouds. Mentioned those on the previous page. Because coal often has about 1 or 2 or 3% sulfur, coal combustion is also a major source of sulfate in the atmosphere, and sulfates from coal combustion might explain that sort of anomalous non-increase in temperature that occurred in the 50s and 60s that we saw a few slides ago. So sulfate can be from anthropogenic sources or it can be from natural sources. What I think is really kind of cool and important is a case study of a volcano that erupted, and modelers use their models to model the effect of the volcano on the climate, and this shows those results. The volcano is Pinatubo in the the volcanic arc of the Philippines. Major eruption in 1991 of Mount Pinatubo sent all kinds of pyroclastic debris close to the volcano, but also exploded a huge ash cloud up into the troposphere that carried a lot of sulfate up with it. So here's the eruption. The black line, the solid line here, I guess is dark gray, is measured temperature. So you can see that Pinatubo erupts, sulfate gets up into the atmosphere, and within a year has decreased average mean global temperature by about 0.5 degree centigrade. It wiped out 50% of global warming in one volcanic eruption. And then, kind of slow recovery back to background. And then different modelers, you could, if you wanted to dig into the details of this paper, you could. Different modelers who have all their different variables. They've got the scattering capacity of sulfate. They've got CO2 in the atmosphere. They've got incoming solar radiation. They got all that stuff. And the point I also seek to make is the good precision of models. And these are old models. These are models that are 20 years old. Climate modelers are pretty darn good. And anybody who claims that climate models are too imprecise to act on climate change mitigation or emissions reductions is out to lunch. It's not a modeling class, obviously. If you want to do a little climate modeling, geology department has a class that I think is going to be offered next year. Who knows what's going to happen next year, but it's scheduled to be offered, called Earth History and Climate, or Climate and Earth History. And I've taught it before, and my colleague Will Amadon, and we do some modeling, some basic modeling, and it kind of gets into those basic parameters like incoming solar radiation, emitted and reflected radiation. This is how much is being emitted back from the Earth's surface, warming bodies giving off infrared radiation. Winds. So the modeling that we do in that class doesn't include winds, for example. But modern day GCMs, general circulation models, or global climate models do obviously have to include winds. Those models include mountains, because mountains are cooler at the top and warmer at the bottom, and they deflect airflow and they trap precipitation by the orographic effect. So mountains are important. And weather systems, the movement of materials, the evaporation that puts water into the atmosphere. Dynamics on land, is CO2 being fixed by photosynthesis into plants and then by decomposition into soils? Or is the land a net source because forest fire just released a huge amount of carbon into the atmosphere? So the land dynamics are important. Oceans, obviously, 70-something% of the Earth's surface have to be a huge variable in any climate model, including the currents that transport heat, transport carbon all over the Earth. Heat transfer, if the atmosphere warms, the ocean will absorb some of that heat by the first law of thermodynamics. So you would have to include like rate of warming of the ocean or rate of transfer of heat from air to ocean. Yeah, and dynamics of water vapor tied into weather, evaporation, transport of water vapor, and so on and so forth would all go into a climate model. So, climate models are probably complex at some level. Obviously they are. I can't sit down and write a good climate model off the top of my head, but I can understand conceptually what goes into a climate model. And if I wanted to critique somebody's climate model, I might say, what is your value for incoming solar radiation? What is the greenhouse gas factor that's trapping emitted and reflected radiation, etc. You get the idea. So, this is it. Last slide. Back to the same old systems map. And, carbon dioxide and sulfur in the form of sulfate come out of volcanoes by volcanism. A certain amount of carbon is naturally released by decomposition, by chemical weathering, gets into the atmosphere. But the rate at which humans are forcing carbon from the lithosphere or crust of the Earth into the atmosphere is orders of magnitude greater than the natural flux. So it's accumulating in the atmosphere, and that's forcing it into the oceans. The natural rate of fixation from carbon from oceans to seafloor, eventually into the crust of the Earth. Well, look at that rate. That rate is not, the natural rate is simply not going to suffice. And I guess you could say if we completely cut off all carbon emissions, it would, you do some math, I think it would take at least 50 years to deal with it, ignoring all kinds of complexities. It would take 50 years to get back down to some normal steady state by the natural rates. But these rates of burial of CO2 into the lithosphere of the Earth, photosynthesis as a fixation method for getting CO2 into ecosystems, into soils and out of the atmosphere, and also chemical weathering. The weathering of rocks at the surface also fixes carbon into soils or groundwater. So this diagram also provides us with some windows. Cut down emissions, increase fixation or sequestration, and we are on the right path towards a better carbon future. So there's one more presentation coming up. If I can get ITS or the computer people, the Library and Information Services people, to give us more memory in the Canvas site, because we're maxed. And that's why I have to keep making this video shorter and shorter and better. Except seemingly, I don't know if it's getting better each time I record it. But anyway, I hope that's some useful basics of the climate system. Really just basic fundamental physical, chemical, biochemical, biological aspects to think about when thinking about the climate system. The next presentation, powers be willing, will be on impacts of climate change and looking at some solutions to climate change.